Welcome to our second part of strength properties of soil. So today we are going to look at the trioaxial test. The trioaxial test is very important to model the condition in the field. How is that done? So previously we looked at the direct shear test. For direct shear test, we said it has a limitation of such that a limitation of failure pane of being predetermined. Remember, I said that the failure pane is predetermined. While for such a test, a soil may fail at any plane. Is that okay? Due to application of loading. So for the trioaxial test, the soil samples are used in this test as cylindrical, with a ratio of length to diameter of 2. Is that okay? Length divided by diameter, you get 2. So normally they are 38.1 millimeters in diameter and 76.2 millimeters in length. It is loaded under condition of axial symmetry. So this material, in this experiment, we load soil in two conditions, or under two loadings. The first loading is what we call the isotropic. The isotropic loading. In such loading, what we call the consolidational loadings. Now we consolidate the soil. So the soil in such a test, we apply the confining stress, rho 3. Is that okay? Now for when this stress is applied, a material either can be allowed to drain. When there is drainage, when there is free drainage, then that is called consolidation. Consolidation. Consolidation, is that okay? Consolidation. Now, water, the consolidation is under condition under which when there is reduction in the dimension, the volume of the sample by expulsion of water, or repelling expulsion of water. The pore water pressure reduces, or water moves out, or unconsolidated. Unconsolidated, it occurs when the pore water pressure, the drainage here, the pore water pressure is locked, the valve is locked. Therefore, there's no free drainage. So in these two cases, you can both measure deformation. The first case of consolidation, you put sensors to measure the lateral deformation and also the axial deformation. While if that is for unsaturated soils, is that okay? Unsaturated. But if the soil is saturated and the drainage lines are under consolidation, therefore water is allowed to go out, then you measure the amount of water. This amount of water which goes out of the sample when apply the symmetric loading, or what we call the confining stress, will be equal to the volume in a reduction of the sample. Is that okay? Now, for the volume of water which you collect here will be equal to the deformation which has occurred, the volumetric deformation which has occurred. Is that okay? So, but if there's no consolidation, therefore the drainage lines are locked, therefore, and the sample is saturated, therefore this material cannot deform. Is that okay? The material cannot deform. So for such conditions, for completely saturated material, normally we don't incur the conditions of what? Of axial loading. Is that okay? No, they're normally discovered because under this condition there will be no volume change, because if the material is consolidated and the water, remember water is uncompressible. You can't compress water. So those are the three ways you can apply, you can carry out this test. Now this test can be carried out in three conditions, and the first condition is consolidated and drain, which we call the CD. Consolidated, you consolidate, then failure occurs, shearing occurs under conditions of drainage. Is that okay? Under condition of drainage. It's still under application of this axial load, simultaneous when you're applying the confining stress, and the failure occurs also under conditions of free drainage. Is that okay? So the next one is consolidated and drained. In such condition that under the first case of isometric loading, isometric loading, and under the condition of isometric loading, before compression loading, the soil is consolidating. But when you now apply the axial load, that is compression loading. Is that okay? When you apply the axial load, compression loading in the second phase to cause shear failure, through a piston. Through a piston here, what happens in such condition that the consolidation, which you call the CU, consolidation undrained condition, failure occurs under undrained what condition? Is that okay? Then the last one is unconsolidated and drained. What happens that for such soils, normally they are not what? You apply, you don't apply the what? You don't apply, there is no consolidation, there's no isometric what? Isotropic loading. Is that okay? There's no isotropic compression. So what happens that you apply the axial load, then you apply the confining stress at the same time. For in such a case, rho 1, rho 3 will be 0, as we shall see. Is that okay? And under that condition, the material fails under, there was no drainage, there was no consolidation, and also there was no drainage. Shear occurs in such condition. And this is very common in swamps or in either consolidated what soils. So how do we do this test? We have shown the 3D condition we can do. So this test is done the way they say that you apply the confining stress after achieving conditions of drainage. Is that okay? Or the consolidation after full consolidation has occurred, therefore there is no more pour water coming out. When the load has fully, then you apply the axial, what we call the compression loading. Is that all the axial load? So now this is what you do here. You apply the confining stress and under the condition of, then also if it is CD, then also you apply the axial stress. When the material shears, then you record the sum of these prices will give you this, which we call the major principal stress. Now for this one, it's called the minor principal stress. This is a major principal stress. Then after that, you increase. You repeat the experiment with increase in what? With increase in confining stress. When you increase the final stress, when the condition of drainage have stopped, or maybe when the consolidation has stopped, then you apply your axial load. Is that okay? You apply your axial load, then you also record when failure occurs under conditions of what? Of drainage, if it is a CD test. Normally, this is normally for sandy soil. Is that okay? Sandy silt, sandy soil. Is that okay? And that's why you have, remember for sandy soil, there will be obviously consolidation. Water will be able to escape. Is that okay? That's why you test under condition of consolidation and drainage. For such a material, you record this, you increase this, then you apply the axial load, then load 2. So that you'll be able, then you repeat it the third time through the same procedure. So you come up with enough. How do you plot? So you plot rho 3, which is our minor stress. Then also you plot rho 1, which is our major principal stress. Then you get the radius, then you can draw this circle. Then you repeat it for this other circle, then you repeat it for this other circle. Then you do a straight line. Now that straight line is a point, it is a tangent to this what? To these 3 circles of stress. Okay, is that okay? Then this one will give what we call the failure envelope. We shall see how the failure envelope is very important. Then where it meets the vertical axis, this scale should be somehow be the same as this scale. Is that okay? Where it meets this vertical axis, it will give you what we call the cohesion. Then the slope, the tan inverse of the slope, will give you the internal angle of friction. So we see that we do this test in 3, and under 3 conditions. The first one is unconsolidated and drained. This is usual, which is a quick test. And under quick test, we say that we don't apply the confining stress, because what we do, we just apply the deviator stress. Is that okay? The deviator stress. And normally you only do one curve. We just only apply through this piston for the axial stress. We don't apply the confining stress, we just only apply the deviator stress. Is that okay? Because why you don't? Because the reason why you don't apply the confining stress, because it is under condition of no consolidation. So when you apply the load under condition of no consolidation, there will be no change. Is that okay? There will be no change. There will be no change because the material you cannot. There will be increase in pore water pressures, but there will be no change. Is that okay? So we just apply the deviator stress under the condition of or still no drainage. Then when failure occurs, that stress which has caused the failure occur, the deflator stress, we record it as our rho 1 because it's 0 plus the deflator stress to give us rho 1. We get this other curve. So under this curve, normally we know one curve is enough. We draw an horizontal curve at it as a tangent of this curve up here. Okay? An horizontal curve here. So normally, the only thing you're timing here is only the cohesion and the undrained shear. Okay? So here we get what called the undrained shear. Is that okay? Which is this one here? And the cohesion will be the undrained shear, which will be the cohesion of that material. Is that okay? Now, for this is suitable for probably to saturation soils, it gives the foundation stability for fully saturated soils. Determine the C. Another test, another condition under consolidation and consolidation it occurs that under the isometric loading you apply the isometric loading. Is that okay? Until normal consolidation occurs. Now, for when the consolidation stops, then you apply the axial load, what we call the compression loading. Is that okay? Or what we call the deviator stress, or the loading, the P. This one here, we apply the axial load until the failure occurs. Is that okay? So when that failure occurs, you can now you can put rho 3 and rho 1. Obviously, that one will give you the cohesion. Normally, this one here, it under so the soil which is normally clay soil. Is that okay? But where there will be somehow drainage. Okay? But failure will occur under condition of no drainage. So usually when changes in moisture content is expected, okay, where there will be condition of what? Of drainage, especially in dams, stability of dams. Okay? Remember, dams there is fluctuation in water levels, so there will be condition of no water and conditions of what? Of water. So you need to monitor to determine the strength in such conditions. It's more usually for clays, where there is free drainage. Is that okay? Where you anticipate that there will be drainage or there will be consolidation. Is that okay? Then you determine the strength under such conditions. Now, pore water pressures are measured. So for this one here, normally we get effective. These are normally effective what? Effective stresses, because you can determine the pore pressure under conditions of no drainage. Yeah? Under the condition of shearing. Is that okay? You can determine the pore water pressure. Therefore, here you can determine these are effective what? Effective stresses. Then the third condition we said is what called consolidation drainage. This is for sand materials. And the samples are consolidated as in previous test. You consolidate by under condition of isotropic compression or loading. But shearing is carried out slowly under conditions of no excessive pore water pressure. So now here, still these are also effective what? Stresses. But still here we assume that the stresses you measure will be effective, because they have fully achieved what we call complete drainage in both consolidation and drainage test. The drainage test is what we call under compression loading, when you apply our loading through the piston on top, the axial load. Is that okay? Then for this one here, normally we don't get, since for sand normally we don't get any cohesion. Is that okay? So usually stable for sand soils. In absence of pore water pressure, the strength of sand